Hi everyone, and welcome to this lesson on the properties of limits. If you think about what you have learned so far about limits, you were introduced first to graphic and numeric methods for finding limits. This lesson gets us more into the algebraic or analytic side of finding limits. What we will be talking about today are some properties of limits which you will see as we soon discuss the algebraic determination of limits. And I think these properties will very much make sense to you. So suppose that c is a constant and the limit of f of x as x approaches a equals L, and the limit of g of x as x approaches a number a is equal to m both exist. Then the limit of the sum of f of x and g of x as x approaches a simply is the sum of the limit of each of those individual functions. Therefore, we have simply L plus m. If we want the limit of the difference between the functions as x approaches a, that simply will be L minus m. And finally, if we have the function f of x, or it could have been g of x, multiplied by a constant c, that limit would be equal to c times L. Again, I think these will pretty much make very easy sense to you. Continuing on, if we want the product of the functions f of x and the limit of that product as x approaches a, that simply will be L times m. The limit of the quotient of the two functions as x approaches a simply will be L over m. And finally, if we have the limit of the function raised to a power, and once again this could have easily been the g function instead, this limit simply would be L raised to the n power. Let's look at a few practice examples for you. In this first one, we have two limits that are provided to us. The limit of f of x as x approaches a number c equal to 3 over 2, and the limit of g of x as x approaches that same number c is equal to 1/2. Notice in all of these properties, with the two functions you are provided information on, notice how you are approaching the same number in each. That does need to be the case. In letter A, if we want the limit of 4 times the function f of x as x approaches c, that simply is going to be 4 times the limit of the function, which was 3/2, which in the end gives us 6. In part B, where we want the limit of the sum, remember that's simply going to be the sum of the individual limits. So we have 3/2 plus 1/2, which in the end simplifies to 2. If we want the limit of the product, we simply are going to multiply the two individual limits, and we obtain from that 3/4. And finally, if we want the limit of the quotient of the two functions as x approaches c, we will have 3/2, which was the limit of the f of x function, divided by 1/2, which was the limit of the g of x function, and that simplifies to 3. Let's take a look at another example. Here we have the limit of f of x as x approaches c to equal 27. In letter A, we want the cube root of that function, so we simply will do the cube root of the given limit of f of x, which comes to the cube root of 27, which is 3. In letter B, we want the limit of the function divided by 18, so we're going to do 27, which was the limit of that function as x approached c, divide that by 18, and we can simplify that to 3/2. In letter C, we want the limit of the function squared, so we simply take the limit, which was 27, and we square that. We can leave it like that or do it out. Unfortunately, I don't have my calculator available. Now the last one is a great example of one that you would see in an assessment that you might encounter. Typically these problems are going to show up on non-calculator assessments, so you must be prepared to do these in your head, and this is a great example of that. Here we want the limit of the function that is raised to the 2/3 power. So we're going to take the 27, which was the limit of the function, and we need to raise that to the 2/3. So remember how we do that. The denominator of the exponent tells us what root of 27 we are taking. So we do cube root of 27, which is 3. We still have the numerator part of the exponent, and therefore in the end we have 9 as our answer. Now if you take a look at the properties as they were stated and the examples we've looked at here, you will notice that in each of these cases we were doing x approaches a number. It should be noted that these properties do apply in the same way if you were to be doing a limit as x approaches infinity as well. One other theorem for us to explore as we talk about properties of limits is one called the Squeeze Theorem. This is often used in a lot of other proofs you might encounter in the calculus. You won't necessarily have to do any problems with it here, but it does help just to know about it and have it in your knowledge base. What the Squeeze Theorem states is if we have a function f of x, the values for which lies in between the values of h of x and g of x for all x's in some open interval containing c, except possibly at c itself, and if the limit of h of x as x approaches c happens to be equal to the limit of g of x as x approaches c, both of those limits equaling L, then the limit of the function f of x, which is literally squeezed in between h of x and g of x, will also therefore equal L. I think it makes sense. I have for you a great demonstration applet of this Squeeze Theorem, courtesy of the Mathematics Department of the University of Minnesota. You'll notice we have a blue function and a green function, and you'll notice this black dot coming down this other red function, and you'll notice it sort of teeter-totters right in between the two, in between the green function and the blue function as we get closer and closer to the origin. So this would be a case in which for the green function, the limit as x approaches 0 is 0. Same for the blue function, the limit of the blue function as x approaches 0 is 0. And this red function that was in between, as it settles in between the blue function and the green function, its limit as x approaches 0 is 0 as well. Again, you don't have to solve any problems related to the Squeeze Theorem. You just need to know about it so that if you encounter it again, it will sound familiar to you. Thanks for watching, and we'll see you soon.